Now we will discuss about the interference figure of the prismatic sections or sections cut perpendicular to it is parallel to optic axis. So we have already discussed the partial section of interference figure. Now we will discuss about the sections which are cut parallel to optic axis, or we can say these are the prismatic sections. These are these sections, prismatic sections, if this is the C axis. So prismatic section figure, or we can say it is optic normal figure, because this is the optic axis, so it is perpendicular to that, so it is called optic normal figure. So optic normal figure or prismatic section figure or section cut parallel to optic axis in case of uniaxial minerals, that figure. When that figure is otherwise called flash figure, because the isogyre, which is a very common feature in interference figures, particularly in uniaxial minerals, that flash figure appears in extinction position and immediately vanishes with a slight rotation of the stage, and again appears when the extinction position is approached. So because of its immediate breaking into two hyperbolas, when a little rotation is being given to the stage from the position of extinction, this isogyre is otherwise called as, or this figure, interference figure of the prismatic sections or the optic normal figures, they are called as flash figures, only because the isogyre breaks immediately from extinction position to hyperbolas with a slight rotation. That's why it is called flash figure. So that we will discuss now. So in this case, the isogyres are visible only at and near the extinction position. What is the extinction position? When the vibration direction of the section will coincide with that of the polarizer and analyzer vibration directions. We know every section, mineral section, presents two vibration directions. If those two directions will be parallel to the polar vibration directions, in that case extinction occurs, and in that position, for this prismatic section or the section cut perpendicular to the optic axis, or the optic axis normal optic axis figure, it is optic normal figure, that figure when it is being observed in extinction position, it presents a isogyre, and this isogyre covers the entire field of view. In all other positions of rotation, the figure consists of colored curves only, hyperbolas. These latter are not circular but nearly hyperbolic and are arranged in 4 quadrants, as in figure 7. This is the arrangement of hyperbolas in 4 quadrants. So in the extinction position, we do not find this type of figure. We find the entire field of view is being represented by the isogyre. This is like this, almost like this. Slight portion of these quadrants that is being seen by the color curves, and the entire field of view is like this. This is totally dark. This is the isogar. This is isogar. So this isogar is seen only in extinction portion, that is when the vibration direction of the section coincides with the vibration direction of the nickels. The number of curves which are distinguishable in white light is less than the number produced in monochromatic light, because in white light the separate curves are replaced by white of higher order beyond the curves representing 4 to 7 order. As we know that the higher order interference colors are not distinguishable from one color to another. They simply appear as white or creamy white. So when we talk about higher order interference colors in the interference figure, these colors they mix up and we do not find these separate curves. Separate curves are not found. That's why in case of white light, because of mixing of the curves, the number of curves becomes less compared to that which is seen in monochromatic light. That thing has been discussed. The exact number seen depending upon the mineral, the perfection of lenses, the quality of eyes of the observer, etc. On that basis, we will be able to see the number of curves. In many instances, only the central portion of the figure, that is within a small circle, is visible. In a small circle, this portion is being visible, or this portion is invisible on many occasions, as in figure 8, because when the section is thin or the crystal has weak birefringence or both, in that case these curves are not seen. Only the central portion is being seen, which is being represented by one color, and that is generally we see that appears to be red. Central color is, for example, red. If the interference color seen when the crystal itself is observed between crossed polars. If we keep it in crossed polars, the color will be red, interference color will be red. And the same thing is seen here. Because of its low birefringence, because of its thin section, very thin thickness is very low. In that case, these curves are not seen, only the central portion is seen in form of red interference color. The two opposite quadrants have the lower interference color than the center of the field of view, and the other two quadrants have the higher color than the center. If the plate is thick or the birefringence is greater, so that interference resembles to figure 7. This is figure 7. If the section is thick, then number of rings will be more, number of these hyperbolas will be more. If the section is very thin, weak birefringence, the central portion will be simply red, these rings are not found, these curves are not found. And this color, red color, is same as that of the interference color of the mineral section in plane polarized light. So, here if you take vertical section, in 45-degree position in white light, you take this section of the quartz, it shows red interference color in the middle and yellow in two quadrants and blue in two other quadrants. As it has been discussed, two opposite quadrants have a lower interference color, that is yellow. In two other opposite quadrants which are higher in interference color, that is blue, and the inside is red. So this side is interference color, the blue, yellow, blue, this center is red. The optic axis always lies in those quadrants which have a lower interference color than the center. So optic axis lies in this quadrant because it is yellow. So this is the quadrant which contains the optic axis. The isosphere of this interference figure are seen in form of a broad fuzzy cross and are poorly defined, and when the stage is rotated, they move rapidly out of the field of view. When the extinction position is reached, they form a black cross occupying the large portion of the field of view. Entire field of view is mostly represented by the isosphere. So this will be isosphere, except these small portions. The entire field of view will be represented by the black cross, occupying the large portion of the field in the field of view. Because why it occurs? Because the vibration direction in all but the outer parts of the four quadrants, entire section except these parts are essentially parallel to the polars. So here the vibration direction is like this, matching with the polars. That's why the extinction condition is reached in these portions, except these portions. So the most part of the field of view is occupied by this isosphere, because the vibration direction in this part is matching with that of the polars, except these small quadrants towards the periphery. So this is the isosphere. These are the, here we see the color, but this is dark. This is isosphere. And this isosphere is being seen when the vibration direction matches with the polars. And with a slight rotation, within a 5-degree rotation, of a slight rotation, the isogar breaks into hyperbola, which are visible when optic axis is at 45-degree position. No isogar is seen. This isogar breaks into hyperbolas, and the hyperbolas enter into that section to which the optic axis moves. Let us say the optic axis is like this in the position of extinction, or in the extinction position it is or the isogar is occupying the major part of the field of view. So with slight rotation, if 5D rotation, the optic axis will occur like this, and this isogar, this black cross will immediately vanish. It will be converted into two hyperbolas, and these two hyperbolas are seen in those quadrants which contain the optic axis, and here the colors are of lower order compared to the middle, and in these quadrants the color is higher. So optic axis contains the quadrants that contains lower order interference color. So when the section is rotated, this black cross separates promptly into two hyperbolic curves which leave the field of view in opposite quadrants into which the optic axis is rotated within a small angular rotation, let us say 5 degree. As the next position of extinction is reapproached to 90 degree, the isogar again enters the field of view as hyperbolic curves in the same pair of opposite quadrants. The quadrants in which the hyperbola were the isogar was broken and was transferred to the quadrants. In that quadrants, the hyperbolas, they come together to form the black cross. They form the cross and leave the field of view in the other pair of opposite quadrants when the rotation is made. So this is 5 degree to 90 degree. And again when it turns 5 degree, then again 90 degree. In this case, the opposite quadrant, the isogar will appear in opposite quadrants because to those quadrants the c-axis moves. So hyperbola appears in those quadrants into which the optic axis moves. The isogar moves so rapidly that this interference figure is sometimes called as flash figure. The optic axis always lies in those quadrants in which the isogars enter and in which they leave the field of view. In 5D position, the breaking is immediate, and in 45D position, no isogar is seen and the field of view is exhibited by the interference colors. If isochromes present are concave outward, the color in the center of the field of view is normal interference color as seen in crossed polars. As you have discussed here, this is normal interference color, and the quadrants which contains the optic axis that presents lower order interference color. This is higher order interference color. This feature can be seen in 45 degree position. In 5 degree rotation, only the quadrants into which the optic axis moves. There we see the figure. There we see the hyperbola. As we move to 45 degree position, only the no isogyre is seen and these colored curves are seen. When the 45 position is reached, it is the position of no isogyre. The field of view is exhibited by some interference colors. If isochrons present, some interference colors, and these are the isochroms here are concave outwards. The color in the center of the field of view is normal interference color as seen in crossed polars. So let me sum up. The optic normal interference figures in extinction position present a black cross which covers the major part of the field of view, and on slight rotation the black isogyre breaks into two hyperbola which appear into those quadrants into which the optic axis moves. And in 45 degree position, what happens? The isogyre is not seen and the quadrants which contain the optic axis, that presents the lower order interference color in the hyperbolas and higher interference color in opposite quadrants, with the interference color in the middle that is same as that of the mineral section which is observed in plane polarized light under cross-nickel condition. It is a case of no isogyre. Isogyre results only when the extinction position is approached. In that position only the isogyre is seen. In other positions isogyre is not seen. And when this interference figure is being seen in extinction position, the entire field is being covered by the black cross. Why? Because we know that if this is the optic axis, we have the rings of light rays, falling, and the rays which are here in this side, they will, to describe the vibration direction, what we do is O ray always vibrates in the basal plane. O ray. E ray always vibrates in a plane that contains the incident ray and the C axis. So this is C axis and this is the incident ray. So they will be contained in a plane like this. So in that plane it will vibrate like this. In this side it will vibrate like this. So in this side it will vibrate like this. It will vibrate like this. So more or less the entire, as we go on to the outside rings, the more and more it becomes flat. So a flat figure, a major portion of the field of view comes under a condition in which the vibration direction of the mineral section becomes like this, which is equal to the which matches with the polar vibration directions. That's why major portion we find that the vibration directions of the mineral section coincides with the vibration direction of the nickel. That's why we get a big cross. So here the vibration direction like this, like this. That's why it matches with the polars. That's why we see darkness. We define isogar at the locus of points where the vibration direction is found to be parallel to vibration direction of the mineral section is found to be parallel to that of the polarizers or to the nickels. In this case happens here. That's why we see that most part of the field of view are being represented by this dark cross. Because if this is the ring, this is the optic axis, so the ray, how we define the vibration direction? E ray vibrates in a plane that contains the incident of this ray is coming like this. This ray is coming like this. It will pass through the plane. This is the optic axis and this is the circle in which the light is falling. We have to imagine a plane that will contain this optic axis and the incident ray. So the plane will be oriented at some inclination to the horizontal plane. So in that plane the vibration direction of E will be like this. Then O will be like this. In this side it will be like this. It will be like this. So that's why we get a field of this type which is totally dark. So you only see the the colored curves in this position. So that's why it has been discussed that the black cross which occurs in the position of extinction so occupies a large portion of the field of view because vibration direction in the all parts except the outer parts of the four quadrants where they are essentially parallel to the polars. That's why we got a big cross, big dark cross covering the entire field of view. Upon slight rotation, say 5 degree, isogar breaks into hyperbolas which are visible in this side, into which the optic axis moves into those quadrants. So when optic axis is at 45 degree position, no isogar is seen and field of view may exhibit some interference colors. This portion, particular central portion, if isochromes are present there, are seen to be concave outwards. The color in the center of the field of view is same as the interference color seen in closed polars under plane polarized light. So this is a case when we talk about the sections that are cut parallel to optic axis. These sections are placed over the stage of the microscope like this with C-axis in this orientation. So this is the optic normal figure which presents isogar in this form covering the most part of the field of view. But if we take any oblique section, any section, here the optic axis is like this, and when that section is being placed over the stage, the optic axis is found to be oriented like this. Then we have to remember that always optic axis indicate the position of melatope, to which the four arms of the isogar they join. And if the inclination will be very high, then it will be out of field of view. Then simply the arms, one of the arms will be found to be sweeping the field of view as the stage is being rotated. This happens when you talk about the oblique sections. Sections cut, oblique sections which are cut oblique to optic axis. First we discussed the section which are perpendicular to optic axis, that is basal section interference figure or optic axis figure. Then we discussed about the sections which are cut parallel to optic axis, or it is called the flash figure. Then we have the oblique sections where the section is cut in such a manner that it is neither perpendicular nor parallel to that of the optic axis. These sections will be called oblique sections. This section, this section, this section. So these are the different sections. These are the different sections. So optic axis is occurring like this. So this section is section which is almost nearly parallel to the basal section will contain the optic axis. This section will contain the optic axis to a major portion. If it is almost 45 degree, it will also contain. If it is nearly vertical, the optic axis will be almost vertical, and this optic axis will not be seen in the interference figure. Here it may be seen, here maximum portion will be seen. And when this section is placed over the stage of the microscope, the optic axis is either this or like this or like this. Varies. So if it is highly, it is almost parallel to the basal pinacoid. It is like this. Optic axis is passing like this. So if I will place it over the stage, the C axis will be almost like this. So the interference figure that will be produced will contain this as the melatope, here the arms of the isogar, here the arms of isogar. When this is being rotated, this optic axis will make a rotation, will show a rotation like this. It will form a cone-like body. So along with this cone formed by the optic axis, the arms they move. If it is not seen, then one arm will be seen. Out of the 4 arms, one arm will be seen, and with rotation the other arm will be seen, and with further rotation the third arm will be seen. Like this it will be seen. So depend upon how much inclined the plane is with respect to the C axis, the melatope may be seen or may not be seen within the field of view. So if the axis of the crystal is perpendicular to the section, the center of cross is on the axis of the microscope, and no matter whether the slide is displaced laterally or stage is rotated, neither the bar nor the melatope in the interference figure will change their position. This is the case when we talk about the basal section interference figure. If, however, the optic axis of the crystal is inclined to the plane of the section, the case becomes somewhat different. The line along which there is no double refraction is now no longer in the center. Which line is the line of no double refraction? We know optic axis is the line along which if light moves, it will suffer no double refraction. There will be darkness in cross-nickel condition. So here when it is the oblique section, this line of double refraction is no longer at the center but is displaced to one side. On either side, at unequal distances, at the positions of one wavelength retardation. We know if the dark cross is like this, here is the one wavelength retardation. Here it is 1.5 wavelength retardation. Here it is 2 wavelength retardation. So this is normal case. So if it is shifted, it should be like this. It should be like this. Optic axis is here. So displaced to one side. On either side, at unequal distances are the positions of one wavelength retardation. One wavelength retardation will be here. It is unequally placed. Here it is symmetrically placed. The figure seen under microscope is now not symmetrically placed in the center of the field of view, but lies to one side. lies to one side. And the rings A dash, B dash, as we are getting in Basal section interference figure, forming curves which are not perfectly true circles now around it. At the stage of the microscope is rotated, the optic axis describes a cone. The interference figure has moved by a rotation to the right successively through several positions. When the inclination of the is slight, the bars remain practically parallel to the vibration planes of the nickels. As I was discussing here, if we take sections, this section, it will contain the optic axis with a slight shift. When the inclination of this is slight, the bars remain practically parallel to the vibration planes of the nickels, or the bars of the isogyre. These are the bars of isogyre. And the center of the cross moves in the same direction as that in which the stage is rotated. If the stage is rotated like this position will rotate like this, because it is almost near the center. If the inclination of the optic axis is great, the bar may appear somewhat curved. This will appear here, it appears curved. So this is for the case when the inclination of the plane is low and the c-axis is nearly vertical through these sections. So this is the place where c-axis appears. So with the rotation 45 degree, this shifts to this position. Again with 45, this will shift to this position. Again 45 it will shift to this position, like this. 45 degree, 90 degree position. So clockwise rotation of an off-centered optic axis. This is called off-centered optic axis figure. Why? In case of centered optic axis figure, that is the case when we talk about basal section. The optic axis occurs at the center. When the section is not cut perpendicular to optic axis and is not parallel to optic axis, in that case, depending upon the inclination of the optic axis to the plane, we get off-centered figures. So here the optic axis, in this case, the optic axis will be seen like this, little shifted a little to this side. If it is highly oblique, in that case, this will have somewhere here, the optic axis will be here. So in this case, when the optic axis is totally out of field of view, in that case these straight bars of isogyre, they may be found to be bent. It will bend. This is showing slight curvature of the isogyre. So whatever great the inclination of the section may be, the isogyres are absolutely straight and parallel with the planes of the nickels when they pass through the center of the field. On rotation, on either side, on either direction, they curve so that the convex side is toward this straight line position. Convex side, they will be bent like this, but this convex side will be towards the So this is the straight position. It bent like this. This is the straight position. If they are bent, they will be bent like this. They will bend like this, convex. They will make convex like this. Figure 12. Like this. Convex. Here it is the melatope. So when you talk about the interference figure of uniaxial minerals, the basal section interference figures are highly useful because of their symmetry and because of the symmetrical occurrence of colored rings displaying the Newton scale of interference colors from the center outwards. Similarly, flash figure is also important because it can indicate the fact that the position of optic axis is parallel to any one of the polar directions when the dark cross covers the full field of view is seen. With slight rotation, the optic axis shifts to the quadrants into which the isogyre breaks into hyperbola, and hyperbola appear in those sections, those quadrants into which the optic axis moves. So, flash figure will indicate the position of optic axis easily, and oblique sections, they, because of their uncentered position of the melatope, they can clearly identify the fact that the section has not been cut parallel to optic axis or perpendicular to optic axis. It is somehow oblique to the optic axis. Now I will discuss about the uses of interference figure, uniaxial interference figure. The most use of this interference figure is to determine the optic sign. That is the main use. Besides that, we can determine whether the crystal belongs to uniaxial group or biaxial group. That we can know. Whether the section is cut parallel to basal sections or not, that we can know. Whether the section has been cut parallel to C axis or it is a vertical section or not. In case of uniaxial minerals, that we can know. We can locate the position of the optic axis in a section. We can determine optic sign, and in order to determine optic sign, we have to remember that radial lines, this is isogyre. So we have this is isogyre like this, thinnest at the melatope zone and gradually thicker outwards. So it is like this. So here is thinnest, then gradually thicker. So this is the figure, and we have the colored rings, we have the colored curves, and E is always radial. E vibration direction is always radial. E vibration direction is always radial. E vibration direction is always radial. O is always tangential. Anywhere you take, O is always tangential. This is O. this is O, 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 and E is always radial. Why? Why? Let me discuss about that. We know E ray always vibrates in a plane that contains the incident ray and C axis. So when you talk about a basal section, in that case the C axis is like this. The rings are placed like this. The ray of light is coming from bottom. So the C axis direction to which the ray is parallel. So this will be a plane in which the E ray will vibrate. So E ray will vibrate in this plane. That means it will be radial because E ray will vibrate in this plane. So E ray will be radial. What about the O ray? O ray always vibrates in basal plane and perpendicular to E. So if this will be the O ray always vibrates in basal plane. So in this section, O ray basal plane means it will vibrate like this. It will vibrate like this. It will vibrate like this. It will vibrate like this, because it will be contained in the basal plane. But this is the vertical section in which the E ray will vibrate. So E ray will be radial, O ray will be tangential. This fact we have to remember. By remembering this fact, we can be able to deduce whether the basal section interference figure is providing positive sign or negative sign, because when a accessory plate is being pushed, let us say it is pushed with this direction slow, so this will be fast. So with length fast, let us say gypsum plate is pushed. So with length fast it is being pushed. So it is parallel to E vibration direction. If color will be blue here, here it will be yellow. That means blue means that it is a case of rise. So this is the fast direction of the accessory plate and this is the E vibration direction. So fast case will be rise. So E will be fast, because this is the fast direction of the accessory plates. Fast they match. So that's why the color has been more. So E fast, O slow, this will be negative. This will be negative in case. Let us take another example. Suppose the accessory plate is presenting, this is the slow direction, let us say. This is slow direction, it is fast direction. This is fast. So now the slow of the accessory plate is parallel to the E vibration direction. If it is blue here, it is yellow here, then here blue color has been possible because of the slow of this accessory plate and the slow of the E ray. So E ray is slow rise. So O will be fast. That means positive. So we have to remember that the radial lines are always always indicative of the E ray vibration direction. Tangential lines, they are the direction for the O ray. So these facts you have to remember, and then we can make use of this interference figure. And this radial line or tangential line, that is only that comes into picture because of the very way that O ray and E ray vibrate in the mineral sections of the uniaxial minerals. That is all about the interference figure, uniaxial interference figure, and how it is being used, that I discussed. Thank you all.